topic for this lesson is inductors in series and parallel. We'll first discuss the series arrangement of inductors. The circuit shown consists of three inductors in series connected across a voltage source E. Each of the inductors experiences the same rate of growth of current, delta I divided by delta T. Thus, V1 is equal to minus L1 times delta I divided by delta T. And the other two voltages, V2 and V3, are developed similarly as shown. Using Kirchhoff's voltage law as shown, and substituting the values of V1, V2, and V3 in the above equation, we get E is equal to delta I divided by delta T times the quantity L1 plus L2 plus L3. Representing L1 and L2 and L3 by L sub T, the total equivalent inductance, we get E is equal to delta I divided by delta T times L sub T, or E divided by L sub T, which is equal to delta I divided by delta T, or the rate of growth of current. For inductors in series, the total inductance is equal to L1 plus L2 plus L3. For n inductors in series, the total inductance is equal to L1 plus L2 plus L3 plus L sub n, and therefore the total inductance is equal to n times L. We observe that inductors as well as resistors in series are governed by the same formula. Now let's turn the discussion to the parallel arrangement of inductors. The circuit below consists of three inductors in parallel connected across a voltage source E. The total rate of growth of current in the circuit is the sum of the individual growth rates for each of the inductors. Thus, the three current equations are developed as shown, and the total rate of current growth is as shown, which is equal to E divided by L1 plus E divided by L2 plus E divided by L3, or E times the quantity 1 over L1 plus 1 over L2 plus 1 over L3. Again, if the total equivalent inductance is L sub T, then 1 over L sub T is equal to 1 over L sub 1 plus 1 over L sub 2 plus 1 over L sub 3. Thus, delta I sub T divided by delta T is equal to E times 1 divided by L sub T, or E divided by L sub T. Considering n inductors, 1 divided by L sub T is equal to 1 divided by L1 plus 1 divided by L2 plus 1 divided by L3 plus 1 divided by L sub n. This equation should be recognized as being the same as the formula for resistances in parallel. Thus, for two parallel inductors, the total inductance is equal to L1 times L2 divided by L1 plus L2. Also, if all inductors are identical, the total inductance is equal to L divided by n. Let's look at an example by considering the circuit shown. In this circuit, L1 is equal to 15 henries, L2 equal 10 henries, L3 4 henries, and E 87 volts. Find the values of the voltages V1, V2, and V3 and the rate of growth of the current. After 4 seconds from the time the switch is closed, calculate the amount of energy stored in each inductor and the total energy drawn from the source. Neglect the resistances of the inductors. The total self-inductance is equal to L1 plus L2 plus L3, or 15 plus 10 plus 4, which is equal to 29 henries. The rate of growth of current is equal to E divided by the total inductance, or 87 volts divided by 29 henries, which equals 3 amperes per second. V1 is equal to 3 amperes per second times 15 henries, or 45 volts, and V2 is equal to 3 amperes per second times 10 henries, or 30 volts, and V3 equals 3 amperes per second times 4 henries, which equals 12 volts. The current I after 4 seconds equals 3 amperes per second times 4, or 12 amps. The energy stored in the 15 henry inductor is equal to 1/2 L1 times I squared, or 1/2 times 15 henries times 12 amps squared, which equals 1080 joules. Similarly, the energy stored in the 10 henry inductor is equal to 720 joules, and the energy stored in the 4 henry inductor is equal to 288 joules. The total energy drawn from the source is equal to 1080 plus 720 plus 288, or 2088 joules.